All right, this page should be really short just because there's no really examples. We're just kind of talking about definitions. So the problem is, does every vector field have a potential function? Unfortunately, it does not. And so let's see how we can determine if we're actually integrating a gradient vector field. First, we introduce a lot of definitions. So the first one, for independence of path. Suppose C1 and C2 are two piecewise smooth curves, which are called paths. They can have the same initial point A and terminal point B. Theorem 2 says that the line integral of a conservative vector field, the vector field which consists of the gradient of our initial function, sometimes called the potential function, depends only on the initial point and terminal point of a curve. That is, it gives the net change of the function. With this terminology, we can say that the line integrals of conservative vector fields are independent of path. So what that means is independent of path is that no matter which pathway I choose to go from A to B, if I choose C sub 1, right, or that's C sub 2, or if I choose C sub 1, I'm going to be getting the same value. So it doesn't matter which pathway I take, I'm still going to have the same values. I could take a new pathway to B. I could go from A to B, on top of the curve this way, and I'm still going to get the same line integral because it's independence of path. The path which I take from A to B does not matter. All right, so that's what independence of path means. A curve is called closed if its terminal point coincides with its initial point. That is, RB equals RA. So again, it's closed because we go from A to B and then all the way back to A. So we've closed this entire pathway. So here you can see that it is closed. And if it's closed, and if we're starting at A, going to B, and then coming back to A, then that total net displacement is going to be 0. So that's why we can say theorem 3, the line integral, again, that's just meaning the line integral. The line integral is independent of path in D if and only if the line integral f dot dr is equal for every closed path, C and D. C representing, our path, and then D is the region. Trying to get off of this pencil, and so we can move down. All right, so since we know that the line integral of any conservative vector field is independent of path, it follows that the line integral is equal to 0 for any closed path. Again, if we start somewhere, we go to a point, and then we come back to the initial point, then, our net displacement, our net change is going to be 0. The physical interpretation is that work done by a conservative force field as it moves an object around a closed path is 0. The following theorem says that the only vector fields that are independent of path are conservative, i.e. the vector field is just a field of gradients. So, theorem 4. Suppose F, again, F is our vector field. So suppose F is a vector field that is continuous on an open connected region D. If the line integral is independent of path in D, then F is a conservative vector field on D. That is, there exists a function f such that del f, so if we take the gradient of f, that's equal to our vector field. We assume that D is open, which means that for every point P and D, there is a disk with center P that lies entirely in D, so we're not closed. In addition, we assume that D is connected. That means that any 2 points in D can be joined by a pathway that lies in D.